Okay, I guess you all have a chance to read this. I posted there. I've been just waiting and waiting and waiting for more people to come in. So I guess I should get started. Just officially informing you, there is actually a university regulation about attendance. I'm not sure if you've been informed in other classes, but I'm going to do it officially in this class today. So if you missed classes totaling 9 hours or more in any class out of 45 hours, then technically you will receive an F. For FA, in more particular, meaning failing because of lack of attendance. So, according to our record, it seems like many of you have been missing classes. Quite a few, you missed many classes. So just a warning. If you have missed 3 classes or more already, and even if you have not missed 3 classes, you cannot miss more than 3 classes. But those who have done so have to attend the rest of the classes starting today. So if someone's not here today, then definitely the person has to petition as to why the person should be let to stay in the class without getting an F. An alternative is for them to actually drop the course. Maybe you find that you didn't do well in the midterm anyways. That's possible. Anyways, just to let you know, we do have this attendance policy, and you might hear more about this in other classes if you haven't heard already. Okay? So this is the serious part. I guess need to get it over with first. Any questions? You understand, right? So I guess I'll be, or Nick will be notifying those who have problems. And then make sure that, I guess, tell them if you know your friend has a problem that they should attend today, come, or file a petition. So the other thing you notice is I posted the assignment. I was going to post it last week, but decided to post it on Monday instead, and still this Friday. So the idea is to give you a chance to look over it. In case you have questions, you can ask me in class before you submit it this Friday. So this is due on the Friday, and you're supposed to submit it by scanning it, taking a picture, whatever, and submit it electronically on Edmodo. Okay, so if you submit late, then you may not be able to do so, and the system will all register that for sure. Okay, so what you will notice, the question may be a little bit different than what Ajahn Ponsai has in terms of my style includes a lot of writing. There might be in the midterm you've seen, but definitely in my exam, you will see texts you need to read, and you need to extract information, understand, and then you have to answer it. Okay, that should be part of your training. This is an English program, and we have, for example, some practical problems describing words which you can use discrete math to help you to solve. Okay, so the assignment covers up to what I taught to last class, but not including today's. So there are very few questions. I think they're very simple, straightforward. So make sure you're able to do these questions. The exam questions would be somewhat different. I'll tell you later, of course. But just give you an idea what to expect or what you should know for sure. Okay, any questions on this? All right, so I'll just start the lecture quite late. So last class we were covering, basically this was the last slide that we covered before I finished. We were talking about functions and relations. And in particular, we left it at finding the inverse, what's called the inverse of a function. And we look at using maybe algebraic rule in terms of an equation like this. And how do we find the inverse? So I described to you, it's very simple. We can simply put this, we have here f of x is 2x plus 4. We just say y equals to 2x plus 4, and then we rearrange it, express it in form of x as a function of y. So I did that in words, and might have shown something on the board last time, very briefly. So in this case, the function is from Q to Q. So what's Q? What's the domain in the codomain? Rational numbers. Rational numbers? Okay? So if you say R is the real numbers, which includes irrational numbers. So this is actually the domain. The first one is the domain. Second one is the codomain. And if you look at it in terms of functional relations that you may be more familiar with, x is the independent variable. That means you can vary the value of x. And then f of x, or y, is a dependent variable. So it depends on x. The y value depends on x. And then when we find the inverse, we're talking about changing it and put y as a function of x instead. Sorry, x, yeah. We'll express y is equal to a function of x here, but then we'll switch it and put x as a function of y. Okay, so in this section, we look at, first start with the composition of a function. So what that means when we have more than one function, how do we combine functions? So the simplest case is when we have two functions, let's say f and g. Okay? So we can say we have female, we have male. Of course, what's common between female and male? Many things. Could be this class, that we have both female and male students. So let's map function f from the domain A to the codomain B. And then in function g, the domain is actually B, which is the codomain in f. And we map it to codomain C. So we can say that these functions, when we say composite, that basically they're integrated or chained together. Or if you use the word compose, because that's the more mathematical term, we will say that the element from A is sent via B codomain to eventually the C codomain. So the notation we use is G composite F. So this is a new function. So this term G with a circle, small circle F, is a function. More specifically, it's a composite function consisting of two functions, F and G. And in that case, what we're doing is we're taking A, translating through B to give you final codomain of C for this function. So previously we defined function like this way. A function has a domain that you map to a codomain. So it's the same format, but the function here is a different notation. This function is a composite function, consists of two functions. Of course, we can have more than two, but for simplicity, we start with just two. and then mapping from A domain to C codomain. So this is for functions, and similarly we can do that for relations. We talked about functions and then relations last time. We define relations, and then we can also map them in the sense of defining a composite relation as well. Okay, so to make it more clear, we'll look at examples. So always help. Okay, let's start out with two very simple domains. A consists of 1, 2, 3, 4, 5. If you want to generalize it, we can say the natural numbers, or n. But let's start with just 1, 2, 3, 4, 5. And then B is lowercase a, b, c, d, e. Or if you want to generalize, if you like, we can say English alphabets, for example. Now we have a C domain. In this case, consists of 8 digits, which if you want to generalize, again, it could be natural numbers. Okay, so let's define a function f. We have two sets, A and B first. So function f will take the domain from A, which consists of 1, 2, 3, 4, 5 in a set. And we'll map it to the codomain B, which consists of, in this case, A, B, C, D, E. So we talked about using arrow diagrams. So that's easy to visualize. You just point your arrow in a directed graph that we have seen before. This is to map to the same domain, but use a directed graph pointing, say, this maps to that. Or something like this. Basically, you have domain, codomain, and you map like this. So this is easy to visualize. But a simpler way to visualize it, which we also shown before, is to show it in form of set of ordered pairs. Okay? So the first element in this ordered pair is the domain, comes from the domain. It's the independent variable you can think of. And then the second one is the codomain. Okay? So we're mapping from this to this to this. So as an example, we can say first one is 1e. So the function will map 1 to e. And the second one, 2b, 3a, 4b, 5e. Okay? So we use all the input, and then we map them to somewhere in the codomain B. Similarly, we can describe a second function called g. In this case, we're using B as a transit domain. So we map from B to C. Okay. So another way to describe the function is actually use a table. So I showed you earlier about the arrow diagram, the set of ordered pairs, and also use of tables. We talked about these before. So in this case, we have y and then g of y, which is a function of y. And we're mapping the ABCDE to this codomain. So these digits are found in this codomain. Okay, so far nothing new. We just define two functions. And we show you two different ways that we have shown you before to represent it. Now, let's find a composite function of g and f. And the domain we're going from A, translating through B, and then to C. So it's A to C. Okay? So what you see, I should show you the full slide. Okay, if we describe this function and we use function f and g like this, the outcome is first domain A is 1. 1 goes to E. And then from E goes to 5. So we have 1, 5. And then 2 goes to B, and B goes to 4. We have 2, 4, and so on. So for all the input in domain A, 1, 2, 3, 4, 5, we have a corresponding output in the codomain C in this composite function to give us this in form of ordered pairs. You can also show this in a table or arrow diagram. Okay, so I believe most of you or many of you have seen this before. You may not have remember. So just a reminder, this is what we talk about. So we can combine functions or integrate them using this composite function, basically. So to make sure that you understand, or most of you understand, let's look at a practice. So this case, we'll define something slightly different, but you have seen before. So let's let A, the domain, be simply x, y, z. So x, y, z, for example, can be used to describe a Cartesian coordinate, like space, x, y, z from some reference point. Or it just can be 3 features of any particular property. Could be, for example, for you would be your gender, your date of, your year of birth, and maybe what else you want to add. So we have basically, age. But your date of birth give you age, it's dependent. So it should be something else. Maybe your height, doesn't matter. For some reason we're interested in those. Okay, so in this case, let's use arrow diagrams. Arrow diagrams for the functions. We'll define 2 functions, C and N. So we're using different notations. Not F and G, but we use C and N here. Okay, so C is defined as, we're going to map from the domain. This is a power set. Remember what a power set is? Power sets is all the subsets of a particular set. Okay? So we're mapping from the power set of A to the domain, codomain of power set of A. So what is the power set of A? So it consists of the null set, empty set, x by itself, y by itself, z by itself, xy, xz, yz, and then xyz. Right? And as some of you mentioned last time in class, which actually assigned it on the assignment for you to prove, the number of subsets is 2 to the power of number of elements, 2 to the power of 3, which is 8. So that's a power set. You're mapping from this to this domain. Now this is a rule that you have seen before. I also showed this in an earlier class. So this is the function with the rule that this function of S stands for set, is the set itself minus the set consists of X only. Okay? So just a reminder, when we start with an empty set, we subtract off the X set, which doesn't exist here, we still get an empty set. And in this case, we start with X, we minus the X set, then we end up with, we map this to an empty set, and so on. So that would be function C. So next, we'll map from the domain power set of A, which is basically these, to a codomain which consists of just the numbers 0, 1, 2, 3. And if you can recognize, basically what that means is number of elements in the set. So if you say null set, that means 0 elements. Has 1 element in here, 1. And this one has 3, and so on. Okay? So this function n of a set S is equal to size of n, or in other words, number of elements in the set. So number of elements 0, 1, 1, 1, 2, 2, 2, 3. And it maps to 0, 1, 2, 3. Okay? Everybody's clear, right? So if you can follow, understand what I said, then it should be clear. Any questions? Okay. So now you know how to do C and N. C function and the N function. The question we're asking you is, which of these compositions makes sense? Are we going to combine it with C circle N, or C compose N, or N compose C? Which one you think makes more sense? Both are possible, let me just say, but one makes more sense. And we're supposed to draw a diagram using this to answer your question. This one, you think makes more sense? Okay, how many people say the second one? And circle C. How many people? Just one person? Okay, let's go back to what that means. It's easy to look at this to see what it means. In particular, focus on this. So should we have C compose N or N compose C? Which one makes more sense? So what we're doing is, with G compose F, that means it's G as a function of F of whatever, say X. If the other way around, then we exchange these two and put F as a function of G of X. So we can have C compose N, or this one. Which one makes more sense? Whoops, too far down. Okay, maybe it's better to look at this. So you know, remember what the C and N is. C is mapping from power set to power set. N is from power set to the size of the set. So what would you get if it's C composed N like this? We just substitute it in. So for example, C of S is this. So instead of S, we'll substitute in N of X. Does that mean something? Or should it be did I do the same thing? No, C, N, okay, yeah. So N, C of X. So we have N of S equals to size of S, or you can say, using N notation, just, well, it's the same thing, but that's what it means. So in this case, N C of X equals to N, and C of X is S minus this. So which one makes sense? So it should be this one, right? Because the inside here, this gives you a set. This is a set. It could be a null set, but it's a set. So you want to find out the size of the set. That makes sense. What about in this case? This is a number. This is a set. So what does it mean trying to remove a set from a number? Doesn't make too much sense. So this is 0, 1, 2, 3, 4, right? So this could be 0, 1, 2, 3, and 4. But this is a set. These are elements of a set. So this makes more sense. The second one makes more sense. So when we look at that, what do we have? We're mapping this minus X. So a null set minus a set consists of X. There's no X in a null set, so you still get a null set, right? Same as before. So the number of elements in a null set is 0. And for X, if it's X, the set of X minus the set of X, then you get a null set again. So this also maps to 0. Y minus set of X, there's no set of X in Y, so still give you Y. So this maps to 1. That maps to 1. x and y, this has x in it, we remove the x. So now the size becomes, this set becomes just y. So now the size of this is 1. Similarly, the size is 1. And this one, there's no x here, size remains 2. X, y, z, we remove the x. So this reduced to size of 2. And that would be this mapping. This composite function of n composing C. I'm pretty sure some of you are confused. Any questions? So we're introducing a composite function. In this case, simply with involving two functions. So for example, C and N. Two functions, C and N. So N is just size of S. N of S is the size of S, number of elements in a set S. And C of S is the set of S, subtract off the element X. And then we talk about this, and the meaning of this simply means C composed of N. That means N of X is an input to C, and you want to map it to a final codomain output. So just to give you further ideas, this exercise is probably easier for you to visualize. So we'll introduce two functions f and g in terms of an arrow diagram. So instead of defining it by equation or table or order set, function f defined by this diagram. So first thing you probably should check to make sure it's a function is what? No two input maps to the same. Well, actually, this maps to the same output. It's okay. Is it? This is fine, but as long as one input does not give you map to two different outputs, right? That's the definition of a function. For the domain, each element in the domain maps to only one element in the codomain. So this is fine. This to 1, 1 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 to 1. So this is a function, this is f, and this is g. So now, can you complete this? Easy, right? So we're starting with g composed of f. So we put f, a goes to 1, and then transiting 1, go to epsilon. So that means a goes to epsilon, right? Very simple. And then b goes to 2, and 2 goes to delta. So b goes to delta. And you can complete this for all the domain which is on the left-hand side of f. And the codomain would be the codomain of g, so which is here. So you can complete that for a, b, c, x, y, z. It's very straightforward, easy to map it. When you visualize it like this, it's very easy. When you have equations, then you have to think a bit harder. Okay? So that could be a simple question to ask, and you should be able to complete that very easily. Another way to ask the question maybe will give you function f and then the composite function g compose f. And we ask you what is g. So what do? We want to find the intermediate. A goes to 1 and A goes to epsilon. So that means we have A transit through something and then go to epsilon. So that means 1 goes to epsilon, right? So you can complete this as well. So this is another type of question we can ask, giving you these two functions, including the composite function. What is g, the function g? So if you visualize it like this, like I said, it's easy in the sense that as long as you take the time, doing it one by one carefully, you can get the answer. Okay? Any questions? Similarly, we can just give you G and then G compose F and ask you to find F. So what do we do in this case? Well, we have 1 goes to alpha. Then what? Then we have to map the alpha to here and trace back. Where does alpha come from? Comes from C. So that means we have C mapped to 1, and then 1 to alpha, that gives you C to alpha. So we back trace this way. 1 to alpha, alpha is here, we back trace, give us C. So this is C to 1. Okay, you can visualize it whatever way helps you to understand. Basically, that's what it means. So you can complete this also relatively easily. This is not difficult. Okay, you just have to be careful. So sometimes, if we want to ask you a trick question, you might put a non-function in here. Then if that's the case, you can just point out it's a non-function. I mean, these are all supposedly functions. F, G, and G compose F. Simple, right? Okay, so let's move on to something slightly more complicated, but not really. So the part that some of you may be afraid of, equations, which are the more likely to be what you see in a function is in form of algebraic equation, like this. Actually, when you're given an algebraic equation, it's actually easier to find. You don't need to do the mapping. All you have to do is manipulate the equation. So actually, it's not supposed to be difficult. So as an example, let's say the function f maps from the natural number domain to the rational number domain. Okay? And the function f given by this rule, f of x equals to 1 over x plus 1. So number x is a natural number. So as a result, f of x or y is a rational number because it's a fraction. And we define a second function g going from here, we're transiting through the rational number domain to the codomain of real numbers. So real numbers includes irrational numbers. So both rational and irrational numbers such as pi or square root of 2. So in this case, the function g of y is equals to squaring y squared minus 1. So two very simple looking functions. So how to define a composite function? Very simple. We say G compose F goes from N transiting through Q, so codomain is R. And we simply embed or put f of z inside G like this, just like we have done here and over there and before. And what that means is we simply substitute f into G. So we want to find G as a function of f of z. So f of z is basically f of z equals to 1 over z plus 1. We just substitute this equation into here, which means we're putting f of z here, we're squaring it and minus 1. So it's actually very simple, especially in a simple case like this. Any questions? Is that too strong, the air conditioning? Blasting. Cannot control it. Okay, so it's an exercise for what I just talked about, composite functions with algebraic forms, in algebraic forms. So we have 3 questions here, 3 parts. We have real numbers as both domain and codomain. So we're mapping from a domain, real number, is a domain, to a codomain, real numbers. So x can be any real number, including square root of 2 and pi and so on. And then f of x, because this is a real number, we also give you a real number. So we're not talking about imaginary numbers because it's only real. Okay, let's look at part B. So make sure that we can all do this. So again, we have 3 scenarios, right? One is we give you both function f and g, and we ask you what is g compose f. So you saw that in an arrow diagram before. Second scenario, we give you f and the composite function g compose f, and we want to find out what is g of y. Okay? So let's look at part B. Right now, all of us, all of you. Can someone give me an answer or tell me what you're supposed to do? Okay, first I ask for volunteers. 2 volunteers. Pick a color. You can answer this on the board. Anybody else volunteering to answer part B? Okay, choose a color. If it's too light, you may want to use this one, just in case. In the meanwhile, you should also work on it yourself. Just either mentally or write it down in your notebook and try to answer part B. If you finish with part B, feel free to work on part A and part C. So this is a good chance for you to work on it individually to show that you understand. So trying to see if you can do it yourself. You can also look for these 2 volunteers to see how they're doing. They haven't finished yet. That means they're semi-stuck maybe. But you can just go ahead. If you finish, it's good. And you can also work on question A and C, parts A and C. Remember what we do in the arrow diagram. That's easy to visualize. But this is now equations. So what it means is you have to manipulate the equations to find the form that you want. So first, they're doing the definition, which is good. You have to do that first part. So how do we solve it? Anybody finish and want to go up there and give them a hand? Any questions? I think you understand the question, right? So using arrow diagrams with the simple functions we looked at, it's easy to find the answers. Now with algebraic equations, it's not difficult, but it takes some thinking. The other thing to think about is, for part B, for example, is there a unique solution? Is it just one solution? Or is more than one solution possible for g of y? So whatever your answer is, as long as you can get the composite function in the correct form, you just double check, then it should be fine. And if you should get different answers, doesn't mean it's wrong. So it's taking you back to algebra. You probably haven't worked with algebra for a while. If someone is finished, feel free to go up there and help them so we can move on. It would be difficult to work this out without pen and paper. So you have to try to visualize if you don't have anything. Anybody would like pieces of paper to write on? Anybody want blank paper to write on? In case you want to practice? Anyone want paper? No? Okay, one person. Okay, I don't have pen. You have to use your own pen. Or find a pen somewhere.
Part A and Part C, but I didn't really get Part B. Is Part C something like this?
I guess we'll get to it, but trying to get Part B. I mean, A would be straightforward.
A was very straightforward.
Yeah. And then C is not difficult, but B may be a bit tricky. So I ask you guys to look at B. You have to solve some equation and trying to rearrange things. So try to keep at it. I mean, if it's correct or not, you can check the answer yourself, right? So if you check and it's not correct, that means it's not correct. So the good thing about this is whatever the answer is for g of y, you can check yourself to see if it's correct. Just put this into here to see if you get this form, given this is f of x. So you can always check yourself in all of these questions. Just do it carefully. You'll see if the answer is correct. So I believe all of you can do part 1 very easily. So just do it. Okay, now we're getting help on both sides. That's good. Finished? Okay, looks like we have one finished part. You can check the answer to see if it's correct and check their methodology, how they actually get it. I guess you can say, unfortunately, this would not be on your e-learning because it's on the board. I didn't put it on here. So you cannot review it later. You have to try to understand it now or write down the answer if you think it's correct. So can you see this side? You can very simply substitute this into here to see if you simplify it to this. I guess the lazy way is just take a picture if everything is correct. Many of you do that anyways. So we're getting close on this side. Okay, so the key here is that a substitution, then you get this answer, which you double check, seems correct. And we have the same. Okay. Okay, so next is an in-class assignment for all of you plus attendance. Working on something you may have finished already, A and C. And you can do that now. That goes over the break. And I will post it on the system soon. So you'll get the assignment in a modal. You have to complete it. So you can, if you need paper, if someone needs paper, you can use this. So the in-class assignment and also attendance is to answer question A and C. So notice I said assignment, not quiz. But you have to answer these two. I just posted on Edmodo. So basically you have until after the break So you can work on it, take a break now, whatever, after the break, say in about 15, 20 minutes, then I'll close the assignment. So it's posted now. If you take a look at a model, and you will answer it in SurveyMonkey, like before. And when I say first part answer, I mean this question. Second part answer, I mean this question, not B. First part, second part, A and C. Now, the only other thing you need to know is how to represent square. So, for example, you can write y square in terms of y star star 2. Okay? You cannot do subscripts or superscripts, not easily that I know of. So just use this to indicate the power of y to the power of 2 for y squared in your answer when you type it in, if there's a y squared or whatever term you have. Because your answer would be an algebraic one, would be in form of, for example, g of z equals to, actually this should be g of y, I guess, to be more correct. G of y equals to y squared plus y minus 2. So you have to put this as g of y equals to y star star 2 plus y minus 2. So this is what you need to input. Replace square with to the power of star star and then 2. Okay, it's break time if you want, or work through the break. Like I said, in about 15 minutes from now, then I'll close the submission. So you can take a break first, come back to work, or finish working, take a break, whatever you like. just make sure you double check your answers. Once you get an answer, especially in part C, whatever FFX is, just test this and this, go through the definition and find out if it agrees with this. You can check to see if your answer is correct. Just be careful. Okay, I'll close the survey in roughly 5 minutes. That means you have to submit in 5 minutes. And then I'll explain to you how to submit or what to submit on Emodo. But the survey on SurveyMonkey will be closed in about 5 minutes. So you have to do that first. If you finish and have not taken a break, just go for a quick break 5 minutes. So just to make more clear, right now you have to complete the Survey Monkey first, because I'll close it in 2 minutes. Then I'll explain to you what to submit on the modal in second half of the class. So if you have not done so, please work and submit on the Survey Monkey link. Have you all submitted? Everyone submitted? Okay, I'm going to close this. Okay, I'm closing it, the survey. I'm closing the survey. Okay, close. Okay, I just closed the survey. We're going to continue the lecture first, and now I'll explain to you when the rest of you come back in what to submit to the modal system. Some of you already submitted something, but I'll explain to you again what you're supposed to submit. So far today we talk about functions and composites of functions. So next we'll talk about composition of relations. So the relations that define a function. So it's given a relation R from domain A to codomain B. So very similar to a function, domain A to codomain B. And say we have another relation S, again transiting from the codomain in A, in R, which is B, to final codomain of C. So we use the same notation, S, compose R, we go from domain A to codomain C. So now let's define that relation. In this case, we say the relation S compose R such that X, the order pair X and Z, is a member of this relation. And the rule is that there's a value Y which is an element of the domain B, which is the codomain for R relation and the domain for the S domain. S for the S relation, sorry. Okay, so we said it's a value of Y such that the order pair X, Y is an element of the relation R, and YZ is an element in the relation S. Okay, so these are notations. In particular, it's a definition. So let's make it more clear. We're looking at an example, and then we can go back and look at it, definition again. So let's define domains again, very simple ones. A consists of 1, 2, 3, 4, 5, B 2, 4, 6, 8, 10, and C 2, 3, 5, 7. So here we have 3 sets. And we define the relations A and B and relations from B to C as these two. So note that a relation may be a function, but remember, in this case, the relation can map a domain input to 2 different values in the codomain output. This relation, for example, R, also S, both of these actually are not functions because of this feature. One is mapped to 2 and mapped to 6. So it's not a unique mapping of one input to one output. So these 2 examples are not functions. But it is a relation. Okay? So as you can see, the composite works very similar to what you already learned in function. Because function is actually, I guess, is a subcase of relation. Relation is more general, you can say. Okay? So we'll use this R and S as the relations. And then we are trying to map the composite. So keep in mind, since it's a relation, again, it's possible for one to map to more than one value in the output. Not for a function. Function is 1 to 1. 1 to 1, right? A relation, 1 can be more than 1. Just like this, 1 to 2 and to 6. Okay, so now we'll continue this. Let's go from level 1 to 2, and then 2 goes to 3, right? 1 to 2, 2 to 3, and 2 to 2. So here we can map 1 to 2, and also 1 to 3. But we're not finished yet. 1 also mapped to 6. And 6 maps to 3 and 7. So what we have here is 1 will map to 2, 1 will map to 3, and 1 will map to 7. Okay, so visually, in form of arrow diagram, it's very straightforward. We can do the same for 2, 3, 4, 5. So with this domain, going to finally, this is the codomain in S. Okay, so you can complete the exercise yourself. So 2 only goes to 4, 4 only goes to 5. So that's easy. So 2 goes to 5 only. And so on. You can do 3, 4, 5. Okay? So this, continue from this example, you can finish it yourself. Okay, again, now we're going into relations. And a relation can map input to multiple output. But this example of a relation is not a function. Because a function only maps one input to one unique output. It cannot be two different ones like this. Okay? So but for relation is okay. Because you're just describing relationship. Now let's look at something more practical, and perhaps that should improve your understanding. Let's try to interpret compositional relations. Example, let's say A is all the students in KMUTT, including exchange students, and so on. So currently, say, and B is a set of all KMUTT courses, which consists of course, computer science courses, as well as general education courses, and other departments in school, they have courses, all different courses. And then we can say C is a set of all the professors or the lecturers in KMUTT. So we have 3 different sets. So as you can see, each student can take, and then you do, I think all of you take more than one course, right? In KMUTT. So that's a relation is fine, but not a function. And then one course is possible to link to more than one lecturer. Like for example, Ajahn Pointsai and I both teach this course. And of course, each lecturer can teach more than one course. Right? Depends how you map it. So now let's define a relation R1 from A to B, such that the order pair xy is this relation. The rule is that the student X is taking course Y. So we can say student X, you, taking this course Y. So we can put your name and CSC165. And that would be a relation in R1. Next, we define R2 relations from B to C such that order pair Mn, the rule is that course M, so it's, for example, CSC165, is taught by Professor N, it could be me, so CSC165 and Jonathan Chan. So what do we have? Do we have R1 compose R2 or R2 compose R1? And what does it mean in this new relation, composite relation? So what do we do with R1, R2? So remember, the general format. I guess it's not really here, but it's close enough. Something like this, I guess. This is G composite F. So if you have R1 composite R2, that means R1, and then we put R2, this in here. Okay, so let's look at the output of R2. R2 we map from B to C. So we have CSC165, Jonathan Chan. And then we'll map it to R1. So what would be the output? So R1 to R2, we go A to C. What's domain C? Professors. What's domain A? Set of students. So in that case, what do we have? We have an order pair of you, the student, and me, in this case, the professor. And for the second case, R2 compose R1. So R1 is this. Is that possible to go R2 compose R1? So one of them is possible because, remember, A to B and then transit to C. But if it's B to C, this is C. C cannot transit to what? Okay, so which one's correct? Relations are A to B, S, B to C. Then we can define S composite R. S composite R means we're taking the input from R first, A to B, and then we put that into here as a function or as a relation, put it into S, such that you take the output from there, from B, go to C. So that is S composite R. But if it's R composite S, it would mean, is that possible in this case? Not given these domains. Because this domain means if it's R composite S, you take this first, B to C. And then you try to take C, which is the output, as a domain input into R. But the domain input in R should be A, not C. So this cannot fit into there. So in this case, given this, we cannot have R composite S. Has to be S composite R. So similarly, which one makes sense then? we have to take student, the output is the course, and then we can map the course to a professor. If it's the other way around, we have a course and a professor, but the professor cannot map into here. It's a different domain. So is it R1 composite R2 or R2 composite R1? It should be R2 composite R1, right? You take R1 first, X to Y, or A to B, and then you put that into R2, which is B to C. So it should be R2 composite R1. And this is not possible given these domains. So what does it mean for this new pair? So we relate you to me. So the meaning is, I am one of your professors. That's what it means. Since you're taking a course from me, you're a student of mine, that means I'm one of your professors. You can take other courses, you have more than one professor. Even in this course, you have 2 professors, but I'm one of your professors. So this is what this means. So it would be the order pair, first one is you, second one is professor. So this student is a student of this professor, or this professor is one of the professors of the student. So that's the interpretation. Okay, so before we move on to section 4.3, one other thing you need to do, it's not updated, but some of you turn in something in Omodo. You also need to submit something to Omodo for me to assign you a mark on Omodo. So what you need to do, even though you have finished the quiz, so what I want you to do is, if you click on this, it should say close, right? If I have internet, it should tell me it's closed. Or if you still have the page, whoops, yeah, it says the survey is currently closed. Please contact the author of this survey for further assistance. If you're still on the page where you submit, then do you know how to take a snapshot of the screen? Do you all know how to take a snapshot just on your screen? Take a snapshot of the screen if you have the answer page and submit it electronically to Emodo. And if you don't have the answer to the screen anymore, and you click, you'll get this, then take a snapshot of this and submit it to the system. It's fine. So to complete your assignment, you need to submit something to Emodo, because I'll provide you with a grade on Emodo. So to complete that, if you still have your SurveyMonkey screen, go to there, take a snapshot, and submit it to Emodo. If you don't have it anymore, then just click on the link and you'll get this. Fine, just take a screenshot of this and submit this to Emodo. Is that clear? So either you submit a screenshot of your answer, if you still have it, to Emodo, which is fine, or you submit a screenshot of this showing that the survey has been closed to Emodo. Either case, I would have your answers because I can see SurveyMonkey answers. But just to complete your assignment upload to Emodo, take a screenshot Anybody not know how to take screenshot? I think everybody knows by now. Anybody not know how to take a screenshot of your phone? If you don't have a phone, I guess, take a screen capture or something. If you're using your computer, screen capture is a bigger file, obviously, but screen capture of a phone is a much smaller file than screen capture of a computer screen. And then when you do a screen capture, that would be in terms of a file. That file is a picture file which you can upload to your assignment in a Moodle. So it's a practice of submitting the assignment you need to do for Friday. You can do that today, the one that's due. The time here is a bit tricky because they don't go by the local time. So don't worry much about the time. Just turn it in, click and submit a link for file. Let's see if more of you submit it. Okay, 9 people turn it in. It was 4 before, so another 5. So the rest of you need to do that sometimes before the deadline of end of today. You can do it now, then you're done. But if you don't want to do it now or you don't know what to do, you still have until the end of today. Make sure you understand what to do and submit it on a Moodle. Any questions? Okay, the reason I asked you to submit your Moodle is because I'm going to give you your marks for your assignment on a Moodle. If you don't submit anything there, I cannot give you a mark. But I can see your answers from SurveyMonkey anyways. So that's not a problem. That's why I said you can even just submit a screen capture of this. That's not a problem. But if you want, I think some of you submitted the actual answer. So if you want instead, fine. You can create a file with the right answers, whatever it is, and submit it. That's also acceptable. So you have until the end of today, 5:45, to submit it to the Moodle system as well for the in-class assignment. Okay, I'll just continue the lecture. If you have questions, you can ask me afterwards. Okay, let's move on. I'll see how much I can cover. Okay, so at the beginning I reviewed inverse of a function. That means it's invertible. So we say a function f is invertible if there is a function b such that we'll use the notation f to the -1 for the inverse. And the domain would be, instead of A to B, it would be from B to A. Such that if the relationship, the rule is f of x equals to y, then f inverse of y equals to x. And this is if and only if. So if this is satisfied, then we say f minus 1, or f inverse, is an inverse of f, the function f. So we have shown you that this is the case. We have this, we rearrange it and express it in terms of f of y equals to x. f of y equals to x. So this, for the same value y, for this value of y, when you substitute into here, when you take the inverse, it will give you back x. If it does not give you back x, that means it's not the inverse. And it has to give you x for all cases of y. More definitions. So this is the part that you need to pay attention to or study up afterwards, especially before exam. So the meaning of onto, one-to-one. And then we'll see how this relates to invertible, if you can find an inverse or not. So first we'll define a terminology called onto. So we said function f, or any function, is onto if everything in the codomain is an output of f. So function f, all the inputs it has, all the inputs maps to all the possible outputs. So all the outputs of f are in the codomain. So if you have finite input, then obviously the output cannot be infinite number. It has to be finite. If you have infinite input, it's possible to, of course, the output can be infinite. Okay, we'll look at examples to make it more clear. Now, the second definition is, for function f, is one-to-one. So I mentioned this concept before. But in this case, instead of a function saying one input give you one unique output, in this case we're saying one-to-one is if nothing in the codomain is an output via two different input. We cannot have same output, but with have two different input give you the same output. You could for a function, but not for a one-to-one function. So, as an example before, actually that's okay. So when we say onto, so the codomain has elements 1, 2, 3, 4, 5, 6. So this is an example of onto because all of these is an outputs. So there's not a 7 here which has no output. All of these have outputs. So this is an example of onto. This is also an example of one-to-one. Each of these output is unique to a single input. So F is also one-to-one, one-to-one. So all the outputs have only comes from one input. But this is fine, but in this case, in this example, doesn't matter, whatever this function is, this output comes from two input. X and A input will give you the same epsilon. So this function is not one-to-one. It's a function because one input does not give you multiple output, but multiple input can point you to the same output. So in this case, this function is not one-to-one. And also, this function is not onto. because this output, this element in the output in the codomain is not an output. So this function defined this way, all the inputs points to here, but this element has no input. So this example, this is not onto and not one-to-one. Whereas this function g is onto because this output, all of the elements are outputs. So it's onto. And it's one-to-one because each of these output comes from one input. So g is one-to-one and onto. This g composite f, this function, is not one-to-one and is not onto. Okay, these are all functions, but we're defining some properties of a function. In particular, onto when all the outputs, all the elements in the domain, codomain, are outputs. So it's onto. When all the elements, like this one, is not an output, so this function is not onto. And the second definition is one-to-one. That means each of these output comes from one input. So this is one-to-one. This comes from one only, this comes from one only, one only, one only, one only, one only. This is one-to-one. But this one also not one-to-one because this particular output can come from X or A. So, example of not onto, not one-to-one. Okay, so these are definition. So make sure you understand it. And if not, read up to make sure you understand onto and one-to-one. Now, if the function is both one-to-one and onto, that means that function is invertible. It has an inverse. If one of these is not satisfied, then it does not have an inverse. It's not invertible. So as a practice, let's try and look at this and do it together, I guess. We're trying to prove, in this case, we'll give you an algebraic form. The function f mapping from a natural domain to a natural codomain. The rule is f of x 5x plus 7. And we said it's 1-to-1. How do we prove that? So first, what does it mean 1-to-1? Means each output comes from one input. So we can enumerate, just list inputs, natural numbers. So 0, 1, 2, 3, 4, 5, 6, 7, and so on are inputs. Can go into there. 0 goes to 7. So, question is, so 0 goes to 7. Can another value of x go to 7? If it's 1-to-1, the answer is supposed to be no. Only one value of x gives you one value of the output. But another value of x cannot give you the same output. So for example, f of 0 is 7. Is there another value of f of x that gives you 7? if you graph this, visualize it, this is a straight line, right? It's an increasing slope straight line. This is a straight line, fx, 5x plus 7. So visually, you can visualize it. So how does it look like? x0, you get 7. And then 1, you get 12. So 0. So you have a straight line like this, right? So 1-to-1 means all these output value maps to a unique value of x. So how do we find that? Well, if you just invert this, well, that's a different way to do it. But if you invert this graph, you can say, from this, you take any one values of y. I can show you visually, then you can try to prove. We take any value of y, say this one. It gives you one value of x, and this value is unique to this y. Mapping is 1-to-1. So examples of not 1-to-1, say you have sine curve. Value of this can map to this x, or this x, or this x, and so on. So this is not 1-to-1. But the straight line is 1-to-1. So visually you can see it. So now trying to prove it. Okay, this is for you to practice. And the hint, remember the definition, I guess, for all values of x1, x2, natural numbers, if f of x1 equals f of x2, then x1 is x2. That means one value corresponds to 1. That's what we're trying to say. So you can show it in form of a proof. Okay, something for you to work on. And if you have questions, you can ask afterwards or later. So now another practice, we have 1-to-1. Let's do onto. We want to prove that the function g maps from rational to rational numbers. And the rule is gx equal to 5x minus 1. We want to show that this is onto. So what does onto mean? Onto means all the output. Onto means the codomain. The output. All the values are outputs. So in this case, we have infinite number of input, infinite number of output. So can we get all possible or infinite number of outputs? So to answer that, the hint is here. We rearrange it. Instead of having this, we put it in terms of x as a function of y. So we rearrange this, and x is equals to y plus 1 divided by 5. So you can look at the logic here to help you with the proof. So in other words, all possible values of rational number is possible depending on what x is. So to show that's the case, we just substitute, rearrange it, and put y, x in form of y, and then we see that you can look at the argument. And then try to show it systematically, step by step, the proof. But the basic premise is that if you can rearrange it, x equals to this, that means y can take any value of rational number, right? There's no limit to what y can be. If that's the case, y can take any number of rational number. That means this is onto it because the codomain can be any, all the values in codomain are output. Okay, you need to do some thinking and to try to understand this part and try to practice it. And if you have questions, more specific questions, then you can come and ask me or ask your friends. Okay, next let's try to cover the properties of relations. So that part, like I said, it just simply means you need to try to take a little bit more time, look at the definition, what onto is. For finite sets, very easy to visualize. Now we're talking about infinite set, and also for one-to-one. So you should try to spend some time after hours. You're supposed to study, self-study afterwards anyways. Okay, let's take properties of relation. First is order. Okay, so these will be in form of order pairs, like these. So these are 3 examples. So first, relation L. We define a relation, not a function, a relation on 1, 2, 3, 4. And what we like to see is that the order pair xy such that x is less than or equals to y. So that means the first number is smaller than or equal to the second number. So it can be 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 3, 3, 4, and 4, 4. So let's look at the diagram, arrow diagram. Well, actually, it's a directed graph. So if you give this relationship, we start off with 1. 1 is less than 2, so it's an arrow. 1 is less than 3, 1 is less than 4. So satisfy all that. 2. 2 is not less than 1, so the arrow doesn't go this way. 2 is less than 3, 2 is less than 4. And then 3 less than 4. Now, the only thing is, since it's less than or equal to, we have an arrow or circle because this goes back to itself. 2 is less than or equals to 2. So we have these circles here indicating a loop. if we said means x less than y, then we don't have these loops. Because 2 and 2 is not the pair. So this defines order pair. What's the first element? 1. Second element in the order pair. So for example, 3. So 1, 3. And this loop means first element 2. Second element also 2. So 2, 2. Because we have this. So this is how we define this relation. Okay, just the relationship that's given to you. We can visualize this relationship in form of a directed graph. We call it directed because it has directions and it's in form of a graph. Okay, this part may be a bit dry in terms of you falling asleep maybe, because it's also getting late, long lecture. 3 hours is a long time for a lecture, I know. So you do have to study on your own afterwards and try and refresh. And you have questions, ask your friends or come ask me. Okay? But graph theory, which we'll go over a little bit more later on as well, has many applications in computer science. It's very important. Social network connections, search engines, all use graph theory. Second one, relation S on, this is a power set. So this capital P, we're talking about power set. Different notation, but we should be more consistent. Such that x, y, the two elements, means x is a subset of y. So all are subsets of here, such that x, y is a subset of that. Okay, before we do that, let me make more definitions. So we define order relations. The order matters, like the order pair, first one, second one, it makes a difference. Some of the properties we define are reflexive, antisymmetric, and transitive. So these are 3 properties which we will define here are used when you're working with graphs. Reflexive means the order pair XX belongs to the relation for all the x in your input domain. So if you have input x, whatever the inputs are in the domain, you take x and x as the order pair, for example 1, 1, 2, 2, and that would map onto as an element in your relation for all of the x. If that's the case, we call it reflexive. We'll look at an example to be more sure. And the other second one, antisymmetric. If we have order pair xy, that is part of the relation we're defining. If x does not equals to y, if x does not equals to y, that means it's not 2, 2. It could be 2, 3. Then the inverse, yx, does not belong to the relation. If this is satisfied, then it's anti-symmetric. It's another property. And last one is transitive. So this has to do with multiple relations. In the sense that, well, same relation but multiple order pairs. We have xy, and then we have yz. So y and y are the same. So if xy is an output of order pair of this relation, and yz is also the output, then xz, translating through y here, similar idea as composite, is also an element of the relation. So these are properties. If this is satisfied, then this is called transitive. And if all three of these, reflexive, antisymmetric, and transitive, are satisfied in a relation, in the order relation, then it's called partial ordering on the domain A. Because all these, the X is an input, is an element of domain A. Okay, for the second relation, this is an error here, should be diagrammed for relation S. Okay, so we do make mistakes, by the way. So this should be diagrammed for relation S, because we're talking about relation S, which is the second example here. Relation S defined by this power set of ABC, such that this, the order pairs x, y, is that set of x is a subset of y. So instead of A, B, C, I guess we use 1, 2, 3 here, but it's the same thing. 3 elements. So what are the power sets? Again, there are 8 of them because it's 3 elements. Empty set, 1 by itself, 2, 3, and then 1, 3, 1, 2, 2, 3, 1, 2, 3. So these are the power sets. So we can rearrange it like this, and we can do a directed graph again to indicate this order relation. So empty set is a subset of empty set. A set is a subset of itself. Empty set, in fact, is a subset of all sets. So this empty set points to all the nodes everywhere. 1 is a subset of 1, 2, subset of 1, 3, subset of 1, 2, 3, and so on. So this, we're defining this order relation in form of a directed graph. So one property of a graph in computer science, we have a node and we have an edge which connects 2 nodes. And in this case, it's directed graph because the edge points in one direction only, not both ways. Indicates a relationship in one way. And you also see, like I said, a set is a subset of itself. So 1, subset of 1, 2, subset of 2, 3, subset of 3, and so on. You satisfy this being a subset. Okay, for sets instead of numbers, we can also define reflexive, antisymmetric, and transitive. You will see that it's equivalent, but it's easier to read it this way. Reflexive means it's a loop on every node. So if you look at this, loop, 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 loop. So this is reflexive. Antisymmetric if there are no double arrows other than loops. That means arrows do not point both ways, other than the loop. The loop, you can say you can point this way or point that way. We don't put a direction there because it doesn't matter which way it goes. 2, 2, 2, 2. It's the same. So we don't need. So what that means is one direction, one direction, one direction. So this looks to be, if there are no double arrows other than loops, also satisfy. Transitive. If every time you go from X to Z in 2 steps, then there is a direct arrow from X to Z. So you can go from X to Z in 2 steps. This to 3, and then this to here. So this is satisfied in all cases, then it's also transitive. So as an example. So go from here to here, there's an arrow. To go from here to here, transiting here to here, and then there's also an arrow from here to here. So if all cases covering a transition has an arrow directly pointing from the starting node to the end node, then it's defined as transitive. Oh, whoops, down here. Then it's defined as transitive. Actually, I should be showing you this diagram. Okay. I was showing you a different diagram. But okay, so the relations L and S, order relations, again summarizing. You've seen these two before. So this is something that you should do yourself. I'm not assigning as an assignment, but it could be a quiz next week, for example, or something. Could be, but probably not. But so we define a third relation, D. So if you recall, we define 3 relations, L, S, D, which happens to be initials for a drug, of course, but some of you might know that, but it's not the intention, I'm sure. So the diagram for the relation D on 1, 2, 3, 4 is such that AB belongs to this relation D, means A divides B. Do you all know what that means, A divides B? Do you understand this expression, A divides B? So for example, we can say 2 divides 6. Three does not divide 7. So what that means is, if A divides B, B over A is a natural number. It's a whole number, actually a whole number. Doesn't include 0. It should be a whole number. So given this rule, you can say, we want you to verify that this is a partial ordering. Partial ordering means reflexive, antisymmetric, and transitive. So you can show that, draw a diagram just like before. We have diagram for L and S, so draw a diagram for D, which is this relation. It's order relation because the order matters. AB is not the same as BA. So if A divides B, doesn't mean B divides A, right? So 2 divides 6, yes. But 6 doesn't divide 2. So order matters. So this is order relation. It's a relation, and the order matters. So the order pair relation. So for your own exercise, do a diagram, something similar to this, for this. And I can start you off with the nodes. The nodes are 1, 2, 3, 4, 5, 6. So you can start out with 1, 2, 3, 4, 5, 6. And you can do the arrows. And then you can verify that this is a partial ordering. We said verify, not prove. Just to check that conditions are satisfied. Okay, so again, it's a practice. There are a few things I asked you to practice yourself. So try it, because you're supposed to spend time on this course after lecture as well. So that's the time you do practice. So these practice questions may or may not appear in your quiz or exam later, or something similar, but it's a good practice because it would be similar for your quiz and exams later. Okay, so we talked about order relations. What about other orderings? So we show the diagrams with loops. The one that loops to itself. So this is a loop. If 4, 4 is an order pair, then indicate like that. That's a loop. So if the arrow diagram ordering is called strict ordering if there are no loops. That means we cannot have elements AA. We cannot have the same element. Then we call that a strict order. So you do your diagram, you see if the diagram is strict or not. And this strict actually means it's irreflexive. Because remember, in our definition of reflexive, there's a loop on every node. That means it's reflexive. So if we say there are no loops, that means obviously it's not reflexive. And we can also say it's irreflexive, which means not reflexive. Now, another definition you can say, if all the nodes have connections, so every 2 nodes has an arrow between them, one way or the other, then we say the order is total ordering. So for example, this is total ordering because all the nodes want to have connection between one another somehow. So every 2 nodes, all the 2 nodes you can find, all pairs of nodes, has a connection. What about this one? Relation S. Is it a total ordering? And to make it easier for you, I can say it's not total ordering because, for example, the nodes for 2 and 3, there's no connection. Between 2 and 3, there's no connection in any direction. So this relation is not total ordering, but this one is. And both of these are not strict because they're all reflexive, they have loops. Okay, so strict, which also means irreflexive, is not reflexive. Total ordering if all the nodes have arrow connections. So as an example, we define a relation R with the rule that the order pair XY is a relation if X less than Y. In this case, you can visualize it. R is actually total ordering of n. N means if x is in the domain of natural numbers. So you can imagine natural numbers from 0 to infinity, right? So that means all the numbers, 0, 1, 0, 2, 1, 100, 1,000, a million, all of these numbers will have a connection. Because x less than y. So visually, you can argue that, yes, that would be true. So this is an example that is the total ordering for this domain, n. Then you can think about, are there other domains that maybe is not a total ordering? Okay, something for you to think about. Right now we said this is a total ordering on domain n for OX. So I just visualize, you can visualize 0, 1, 2, 3, and whatever, each integer numbers, all of them will link. Are there any domains that may be not a total ordering? Just something for you to think about. Okay, more practice questions, which means you should definitely try them. And if you have questions, I'll be happy to answer you after you try it, not before you try it. So we define a relation on Z, set of integers. The rule is that the order pair is if A times B plus B is odd number. So you can see it's a strange rule, but it's a rule. So for example, 1, 1. 1 plus 1 is not odd. So 1, 1 is not in the relation R. So what about 2, 3? 2, 3, 6 plus 3 is 9. So 2, 3 is part of the relation R. So what you want to do in this practice, determine if this relation that we give you, this order relation, because AB is different from BA, is this relation reflexive, irreflexive? So if it's reflexive, that means it's not irreflexive. If it's irreflexive, that means it's not reflexive. So it's one or the other. Is it antisymmetric? Is it transitive? Okay, so this would be a fair question to ask. That will give you a relation. You're trying to find out if these properties are satisfied. And trying to justify it in some way. Okay, so in terms of more, we can also put it in form of, instead of the abstract form like this, we can just simply give you sets. And the rules are just order pairs like this, for example. So, but it's the same question in the sense that we asked you if this is reflexive, irreflexive, antisymmetric, transitive. So these are all fair questions because it's all possible relations. And you were trying to answer them. So you should try to answer these yourself or work at a group, whatever you like. And the next assignment might have similar questions I'll put on there. But for yourself, if you can do all these, practice, and you understand it, then you have no problem at all in the exam. I mean, definitely will pass. And if you have problems, then you should try to get help. Ask me, ask your friends, ask Ajahn Pointai, whoever you think can help you. But when you come to ask the lecturers, you should try to make an appointment, because sometimes you just cannot find us or we're busy, but just make sure you let us know. You can contact us. In your case, you can just use that motto, I suppose. But if you send me something in the middle of the night, I definitely won't answer. Okay? Any questions? I think that's it. Dismiss in 41 seconds. Yeah, that's the end. So we cover everything, except we didn't do the practice questions because you're supposed to practice them. But we did do enough examples for you to be able to do these practice questions. Okay, so make sure you submit the assignment, the in-class assignment in Moodle if you haven't done so, by the end of today, 5:45. Otherwise, you will be considered late. Okay, 30 of you submitted. That means not all. It's more than 30 of you in the class, even today here.